Hello everyone and welcome back to this next lecture in the DC to DC converter series, and this is where we had left off in the previous lecture where we had simulated the 3-winding transformer, however running at 50 Hz. So for example, if I go over here and I look at the currents and the voltages, we saw that this is how it was behaving. We have 3 windings and we have, since actually this is probably not the best, let me show the voltages instead, this would be good. So since we have a step down transformer with a 2:1 ratio for both the secondary, or rather you can say winding 2 and winding 3, we do see that the voltage in the primary is double the voltage in the 2 secondaries, right, or the secondary and the tertiary. And moreover, we saw that because of the dot polarity of the tertiary winding, the voltage at the tertiary winding is 180° out of phase with respect to the primary and winding 2. So with this, now that we have this transformer running at 50 Hz, the next step is to have this running at high frequency. Now, typically, the frequencies we are looking at, especially for a forward converter or for a flyback or any other kind of DC to DC converter, is usually in the range of around 20 kHz to around 50 kHz. That is usual range. However, for the sake of simulation, I will not be going to that frequencies, because in order to simulate at that frequency, I will need to reduce the integration time step of the simulation, which will only prolong the simulation. So for the sake of this lecture series, I'm going to take the switching frequency as 1000 Hz. But just for your information, that usually switching frequency is never this low. Switching frequency is usually in the range of around 20 to 50 kHz. That is 20,000 to 50,000 Hz. So let me get back to the lecture. So as always, before I start this lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses, and you can visit my own website, which is Python Power Electronics. So if I just go here, you see this is pythonpowerelectronics.com. That is the name of this project, followed by .com. And if you go and learn, you will see this is the list of courses which I have. So these are online courses and you can look through all of them. The very first course is called Simulating Power Electronic Circuits Using Python, and in this I talk about the basics how you can use Python and Python Power Electronics to simulate power electronic circuits. So this course is hosted on Udemy. If you click on this button, it will take you to that link. The second course is Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python in order to design and analyze digital filters for power engineering applications. So I talk about how you can design a low pass filter and a notch filter. Again, the course is hosted on the MOOC website Udemy. You can click on this button to go to the link. And the third course, which is most relevant for this video lecture series, is Simulation of Magnetics for Power Electronics using Python. And in this I talk about how you can simulate magnetic components such as inductors, coupled inductors and transformers for power engineering applications using Python. And there is a case study of how you can simulate a flyback converter with 3 outputs, isolated outputs, using a multi-winding transformer. Again, hosted on the MOOC website Udemy. And the latest course I have is called Control Analysis with Python for Grid Connected Converters. And in this I talk about how you can design and analyze controllers for power electronic applications using Python. And in this I use a single phase H bridge converter connected to a single phase grid as an example to describe all the control concepts. So again, it's hosted on the MOOC website Udemy. So the links for all these courses is provided in the description of this video. If you're interested, please do check it out. So with this, let me return back to our lecture. So what are we going to do? We're going to make a few changes. Let's go over to our circuit. In this voltage source, we now have a voltage source Vn. And this voltage source, if we go back to our circuit parameters, this voltage source is a sinusoidal voltage source of 50 Hz, right? And this is 339 volt peak, which corresponds to 240 volt RMS. Now, we're going to make a few changes. What we're going to do is, instead of just increasing the frequency to 1000 Hz, I would like to emulate what actually happens when you connect a converter. So for example, when you connect a converter, you have a switched voltage, right? You have a rectangular voltage whose pulse width changes. That is how any power electronic converter works. We adjust the pulse width so as to adjust the output voltage, right? Now, in order to do that, I'm going to make a change, and that is I'm going to say that this voltage source, I'm going to replace it with a control voltage source. So before that, let me go over to my circuit and let me copy over these two files. Now that I think about it, let me go to my browser. Let me export the parameters just to make sure that I have the latest parameters, and let me back up my files. So I'm going to copy this, paste it again, copy this, paste it again. So let me just rename this as sine, so that this I know is a sine waveform, and the same goes for the parameters. So just to have a backup of this. So now that we have a backup of this, I can go ahead and change my circuit file. So what I will do, I will change this from a voltage source to a controlled voltage source. So this way I can now generate any voltage I want, and the voltage I want is a rectangular voltage whose pulse width can change. So I'm going to save this, go over to my, because remember I made a change, I must go back to my circuit page and I must click on process circuit schematics. Any topological change, if you add a component, you change a component, you change a branch, you move anything, you must click on process circuit schematics, right? The good part is we don't have any detectable error, so we can continue. Now the edit circuit parameters, because remember we have changed it. Actually I clicked on the wrong one. This is the transformer, I need the voltage source. This is the voltage source. Now you see we have a control voltage source in place, and this is perfectly okay. Now the position is the same. The polarity is also 4A, which is perfectly okay, because we do need the polarity to be upwards. What needs to change, however, is this name. Of course, it's not a very hard and fast rule, but this is more for debugging purpose. So let me call the tag VIN source, right? Usually this should be something unique. It doesn't have to be. It is mainly for debugging purposes, but it's a good idea if you can choose something unique. So now that we have this, let's go back to our main page. Now, what do we need to do? We need to now produce a voltage which is a rectangular pulse. Remember, we've already done some part of this, and that is with respect to our PWM, right? We are already generating PWM. So all we have to do is link the PWM switching pulse to this voltage. And of course, we need to multiply it by some factor so that we produce a voltage. So let's go over to our edit control and let us add a new control file. So let me go first check out if I have a PWM. No, I do not. So I'll go back to the flyback converter and copy the PWM file from there. Yeah, well, this is the gate signal. Copy it and bring it over to the 3-winding transformer. Okay. So let me go over to my editor and check them out. So gate signal, this is 3-winding transformer, this is gate signal.py. So let me just collapse this so that I have more space, and this is what I have. So you see, we are taking a switching frequency of 1000 Hz, we are generating a carrier waveform, we are choosing a modulation signal, which of course we can bring it from outside, but here remember we don't really care for this particular case. For this particular case, all we are trying to do is generate a rectangular voltage. So we can choose this to be a constant, we can just choose it even to be like 0.4 or something. And then we are comparing the modulation signal with the carrier signal, we are generating a gate voltage, right? So now what do I need to do? All I need to do is to change this S1 gate will be my output. However, this output will not be connected to a switch, rather it will be connected to the control voltage source. So let me first, now that this is there, let me go back to my browser and add this file. So make sure in the directory, correct directory, 3-winding transformer, choose the gate signal.py and let me just say here rectangular voltage generation, because that's what we are doing, not really generating a pulse width modulation. This though that's what we are doing, but for this case, this example, we are mimicking an inverter. So let me configure the control. As always, just choose the descriptor because that gets us going quickly. Upload the file, and this should bring us everything. Right now, of course, you see a lot of things have not been copied over, and the reason why they have not been copied over is because the same inputs and outputs were not found in this circuit file. Right, but that's not a problem. What do we need? We don't need any inputs, because remember, all we are generating is a free running PWM. All we need is to generate this output. So this S1 gate, what I'm going to do, I'm going to rename this, and I'm going to call this inverter voltage output. Alright, and I'm going to copy this here as well, and instead of choosing it as 1, let me choose it as 24. Right, so it's basically a 24 volt output. That's what we want. We want a switched 24 volt output. So now what we do, let's go back to our browser and check what all we have. We have the carrier signal, which is very good. We have the carrier signal. We should also generate the modulation signal. It's always a good idea, because as I said, any variable which is not defined at the head of the file as a constant but is used should be defined as a static variable. This is generally a good idea, because otherwise sometimes when you have more complex if and if else conditions, you might be accessing a variable which has not been defined, which might cause your entire circuit to break, simulation to break. So I'm just copying this, and what else do we need? This is the output. So let me copy this over and create an output voltage. So this is control voltage output. Let me paste it here. There's only one, there'll be several targets, because remember there are several voltage sources that we can change. But the only voltage that we are interested is in this control voltage source Vn. Because remember, this is the voltage that we are now trying to mimic as the inverter output voltage. So let's go back to our browser. The initial value can be 0, save it. Now let's go back here and check what else we are missing. We have the carrier frequency, we have the carrier signal. The rest are all constant which have been defined, so we are okay. The only thing is these variable storage elements. So let's come down here. We see that the variable storage elements have also been defined. So what I would do, I would just run this PWM gate signal and see what we get, right? So with this, let's go back to our main page. View output, and let's click on run. Alright, so what I'm going to do is I'm going to create, let's first, of course, we must check on the command line. There is an error, right? This is usually the case. There is usually an error sometimes. And let's see what the error is. It is in this particular statement, PWM gate signal is equal to S1 gate. So let's go to the editor, and you see it is this one. The reason is this variable is no longer defined. If you're trying to access a variable which is not defined, and that means it has not been initialized, doesn't have a value, it's an error in Python. So what needs to be done? We need to replace this. That's all we need to do. So now that I have done this, let me go back and let me run it. Go back to the command line. Now you see there is no error. So this simulation is now running, right? All we need to do now is check if we are indeed getting such a voltage. So I'm going to say inverter voltage, start plot, and let me, where is it? It is PWM gate signal, okay? Because remember, PWM gate signal is what is being equated to the inverter output voltage, right? So waveform legend, let's call this Vin, scaling factor can be 1, and we are done. And let's plot this voltage. Let's go to the file browser, and this is what we have. And you see, we might have to let this simulation run for a while, because remember, we are running it at high frequency, or rather we are running it at high frequency and also there is a PWM, so we could run it again. Yeah, and now you get it. So it's just that we plotted the value too soon. Now you see we are getting a switched voltage, and you'll see that this switched voltage is kind of similar to what an inverter will produce, because this is how it is. So I'm assuming that we have a 24-volt battery. You can of course choose a 12-volt battery as well, or any other battery. You can choose a 5-volt battery, a 9-volt battery, 18-volt, I don't know what all batteries we have. You can choose anything you want, and this voltage will now emulate such a battery connected to an inverter, and the output is a switched voltage. So let me run it once more and see if we get an entire waveform. And let me go back here and check. And as I said, it probably takes some time. But anyway, we'll run it again once more. But in the meantime, now that we have this, the good part is we now have an inverter voltage. So what do? Let's go and change our transformer. So for example, if you come over here, this is a transformer model. We had changed some parameters for our low frequency transformer, that is 50 Hertz. So for example, this is the capacity of the transformer. We had chosen the primary voltage or winding 1 to be 240 volts, right? Now we don't need 240 volts anymore. We need 24 volts because we are connecting a 24 volt switched output, right? So we don't need that much. And similarly, we can reduce this to 12 volts. That is, we can reduce the primary secondary windings to 12 volts. So what we are doing is we are stepping a 24 volt battery output to a 12 volt output, right? And this is quite normal. It does happen quite often. Matter of fact, this is usually what happens when you want to generate either a 5 volt or a 9 volt, right? You would choose a slightly higher winding ratio so that you can step down the voltage. Now the rating, we don't need 30,000 kVA anymore. We can choose 300 VA, right? This is quite normal. Matter of fact, these kind of transformers are very, very standard. You have three winding transformer with a 24 volt and 212 volts and 300 amperes, which corresponds to around 4 to 5 amperes. This is very normal. And then comes F rated. Let's increase this to 1000, right? The reason we are generating 1000 here. So now that we have done this, let's go and plot it again. We might get some more results. And you see now this is an inverter voltage, right? So we can change the modulation signal and we can change this pulse width. This is the advantage of using this method. That is, instead of using just a sinusoid and increasing the frequency, this is actually much better. So now that we have this as well, what is important is this entire circuit has changed, right? We now have a voltage source where we're connecting this switched voltage to the transformer. So we can actually plot all other variables as well, right? So for example, I'm just going to save this so that I don't lose this result. I changes this voltage as 1.png, and let me go and plot the voltages of this transformer, because remember, we are now supplying a switched voltage to the transformer. So let's see how it behaves. And let's go and have a look. And you see this is a new voltage, right? So let's see what we're getting here. See, we have a voltage. I think this is good enough a zoom because we have 3 cycles. You see, the primary, the blue voltage is the source voltage, which is the switched voltage supplied to winding 1. The yellow or the orange line is this voltage, which is stepped down by a factor of 2. And this is the reason is because we're choosing a transformer of 24 by 12 volt, that is 2:1 ratio. So therefore, winding 2 will have a voltage which is half of winding 1, right? And it has the same switching pattern. Winding 3, however, also has the same magnitude as winding 2, but it is completely out of phase, and the reason why it's out of phase is because of the dot polarity, right? Remember, this dot polarity is something that I set when I was designing the forward converter, because in the forward converter, the job of the third winding is to supply power back to the DC supply when the switch is off. So therefore, these voltages are perfectly okay, which means our transformer is now working perfectly okay at 1000 Hz as well. So also, before we wind up this lecture, let's look at the currents. So let me go plot the currents. And let's go back to the file browser. These are the currents. And let's have a look. So let's look again. Again, the usual color coding. Blue is the primary or winding 1. Yellow or orange is winding 2. And the third green winding is third one is winding 3. So when the inverter is on and the voltage is high, you see the blue winding is actually slightly increasing. Alright, there is a slight increase. The reason why there is a slight increase here is that this is when the magnetizing current is increasing. Right? The magnetizing current in the transformer is increasing because remember there is an inductance. And you will actually, if you run it for a long time, you will see that there is an increasing pattern, which means that the magnetizing current takes time to build up. Because remember, flux does not just build up immediately. Flux is the integral of the voltage, and we are applying a switched voltage, which means the flux is going to gradually keep on increasing every time the voltage of the inverter is high. Alright, that is, every time the inverter produces a positive voltage, this flux will keep on increasing, and that's what is happening. It's continuously building. On the secondary side, the minute there is a voltage, it produces a constant current because we have now a pure resistor, and the same goes here as well. We have a constant voltage, right? So therefore, these constant currents are reflected in the secondary as always. As I said before, since it is a step down transformer, we expect the high voltage to have lower current. So actually speaking, this voltage, or rather the current in this secondary winding, or rather primary winding, sorry, high voltage winding, should be half of that of this winding 2 and winding 3. But what is important to understand is winding 1 is supplying the current in both winding 2 and in winding 3. And it is also supplying this magnetizing current. So this is the reason why you will see that this current in the winding 1 appears to be more. I would suggest, if you're watching this lecture, go ahead and try to change the resistance in one of these to a very large value and see how it then behaves. Alright, so with this, we now have a working transformer that works at 1000 Hz. We can now take this transformer and place it in our forward converter. And this is what I will do in the next lecture. So with this, I'm going to end this lecture. If you have any doubts, please do post either in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will include this transformer in the forward converter. Thank you so much for watching and see you soon. Goodbye for now.